Hi everyone. So in this video, this is part 2 of our discussion of ionic bonds and Coulomb's law. So when we gave an example of an ionic bond, we looked at the case of sodium bonding with chlorine. You might remember that sodium has a 3s electron, just one electron, in its s orbital in that third shell, and it's happy to get rid of it because by doing so, then its outermost shell would have an electronic structure of 2p6, whereas chlorine has a 3p5 in its outermost shell. If it can only find some way to get another electron from somewhere else, then it would have a 3p6. And this outermost electronic state is characteristic of neon, and this one is characteristic of argon. And so if sodium can simply transfer its outermost electron to chlorine, then within the bond sodium chloride or halite, then both these elements would have an outermost electronic shell that would approximate a noble gas state, neon in the case of sodium and argon for chlorine. So we want to expand on this a little bit by looking at Coulomb's law. Coulomb's law describes the force of attraction between two charged entities. And so we have a lowercase k, q1, q2, and this distance squared. So k is a proportionality constant. We'll get to that in a moment. So q1, it's rather arbitrary. We'll let q1 be the charge on sodium as a positive charge. q2 can be the charge on chlorine that has a minus charge, just a magnitude of 1 in each case. And then in terms of the distance, chlorine is a larger atom than sodium, so we'll draw it like this, where this fellow is chlorine and this is sodium. The distance would be the distance between the two nuclei. So that distance there is the distance that goes into the denominator here. So it's an inverse square law, a lot like the gravitational force. So the force of gravity, you probably know as this, G times m1 times m2 divided by d squared, where if there's a gravitational force acting between two objects, it's going to depend on their relative masses and how far apart they are. So it's a very parallel, very similar kind of equation. The d squared, you might wonder why that repeats. Well, there's some mathematics to show that the inverse square law is related to the fact that we live in a three-dimensional universe, at least with regards to space. So if we lived in a universe with 4 spatial dimensions, then we would have an inverse cubed law. If we lived in a universe with 5 spatial dimensions, then we would have the inverse law to the 4th power. But we don't live in that. We have three dimensions of space, and so we have inverse square laws. So how about this value k? It has a value of 8.99 times 10 to the 9th, and the units for that are newtons times meters squared divided by c squared. C are units of charge, coulombs. And you can see that if these are both units in coulombs, so if Q1 is a coulomb and Q2 is a coulomb, then that would be a coulomb squared, and that would cancel. And then the d squared, let's say it's in meters, then that would be a spatial unit that would cancel with this meters squared up here, and we'd end up with the net value of force being in newtons. So this proportionality constant k not only allows these two things to be equal, but it's written in a set of units that allows the space and the charge units to cancel out, leaving us something that would be in units of force, which we usually write as newtons.